Hey guys, tonight we slip quietly into one of the strangest ideas humans have ever had, that this universe you're in right now might be only one of many. You're lying there, maybe with your phone glowing softly in the dark, and somewhere, in another version of reality, you might be doing almost the same thing, or something completely different. You feel the slight weight of your blanket, the familiar texture of your pillow, the small sounds in your room, a humming fan, a distant car, maybe the soft breathing of someone nearby. All of this feels so solid, so singular. This is the world, the only one. Your senses insist on it. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Tonight, we're going to let that certainty loosen just a little. Not to scare you, not to confuse you, but to gently explore what scientists and storytellers actually mean when they whisper about parallel universes. And don't worry, you probably wouldn't survive being shrunk down to atom size to check, but well, try it in imagination where it's perfectly safe. Now, dim the lights, and let's ease into tonight's journey together. You start by noticing the phrase itself, parallel universes. In movies and comics, it usually means worlds that sit side by side like pages in a book, universes where history took a different turn, where another version of you made another choice. Maybe there's a universe where you chose a different school, a different city, a different love. That version is instantly emotional and personal, like a hall of mirrors for the soul. Scientists, though, use the idea in a colder, cleaner way. When cosmologists talk about multiverses, they're usually not imagining caped villains or alternate timelines where dinosaurs built spaceships. They're following equations and evidence to their most unsettling conclusions. Some theories, when you take them seriously and push them as far as they naturally go, don't stop at one universe. They keep going. They suggest that what you call the universe might just be one region in a much larger reality. You imagine your universe as a softly glowing bubble, floating in a vast, dark ocean. Inside the bubble, galaxies, stars, planets, the entire sweep of 13.8 billion years of cosmic history. Outside the bubble, not just empty space, but perhaps more bubbles, more regions with their own galaxies, maybe even their own physical rules. The air in your room feels suddenly thinner, as if the ceiling is no longer the limit. It's more like the first page of an endless book. But here's the important part. Right now, parallel universes is not a single, simple theory. It's an umbrella phrase. Under it, scientists place different ideas that arise from different corners of physics. One comes from the way our universe expanded in the first tiny fraction of a second after the Big Bang. Another comes from the slippery rules of quantum mechanics, that strange theory that governs atoms and particles. Others come from speculative attempts to unify gravity with the quantum world, like string theory. Each of these paths leads to some kind of many universes picture, but they are not all the same. Some are basically just big extensions of what we already see, more space beyond the observable edge, with regions so far away that light has not yet had time to reach you. Others are far stranger, suggesting totally separate realms that never touch ours, with different numbers for nature's fundamental constants, or even different underlying equations. You breathe in slowly, letting that distinction sneak into your mind. When a movie says parallel universe, it often means a world you might step into, bump into, or call on the phone with a special glowing device. In real physics, most versions of other universes are not reachable at all. They're not destinations. They're consequences, invisible branches of reality implied by the theories that already explain the sky above you and the particles inside your body. You can picture it like this. Imagine you're standing in a quiet train station at night. You see one track in front of you, one set of rails stretching into the darkness. That's your universe, your timeline, your history. But then, as your eyes adjust, you begin to notice faint silhouettes of other tracks beside it, some running almost parallel, some curving away, some never crossing. You never set foot on them, but the station's blueprint includes them. Physics, in this analogy, is the blueprint. If the blueprint naturally contains other tracks, it may not be fantasy to say they exist. At the same time, you feel a gentle tug towards skepticism. Maybe, you think, we're just very good at making up stories. Humans are pattern hungry. narrative hungry. If one universe is interesting, surely many are more interesting. Maybe our love for multiverse plots in fiction is biasing us, nudging us to favor theories that sound like those stories. It's a fair worry, and many scientists share it. So the first calm step tonight is simply to separate the feelings you have about parallel universes from the claims that physics actually makes. Feelings: wonder, unease, curiosity, sometimes comfort the idea that in some other world things might have gone better. Claims: certain well-supported theories, when taken seriously, predict regions of reality beyond what we can ever observe directly. That's different from saying they're real for sure. It's saying, if this theory is correct, this is what it implies. You let that thought settle, like dust in a beam of moonlight. Science doesn't start with, wouldn't it be cool if? It starts with equations that describe the data we already have, the way galaxies cluster, the faint microwave glow from the early universe, the behavior of particles in accelerators. Only then does it ask, if these equations keep working beyond the part we can see, what kind of bigger structure do they describe? Sometimes the answer is boring. Sometimes it's mind-bending. Parallel universes live in that second category. As you listen, maybe your eyelids grow a bit heavier. You realize that whether or not these other universes exist, this one is already astonishing. Space is expanding. Time has flowed for billions of years. Particles born in the first moments of the cosmos now rest quietly inside your bones. If there are other universes, they don't take meaning away from this one. They simply stretch the canvas on which meaning can be painted. Maybe the universe or multiverse just loves to repeat patterns. Bubbles in boiling water, bubbles in cosmic inflation, branches of a river, branches of quantum possibilities. Tonight, you don't have to decide what's ultimately real. You only have to stay curious, to let the boundaries of your mental map soften a little, like watercolor edges bleeding into the paper. The rest of our journey will wander through the specific ways physicists think many universes might happen. But for now, you rest in this gentle in-between. One world certain, others possible, all of them wrapped inside your sleepy, wondering mind. You drift outward now, away from your room, away from the city lights, as if your thoughts are hitching a ride on a beam of starlight. The universe around you goes dark, then slowly fills with points of fire stars, then clusters of stars, then great hazy rivers of them we call galaxies. You keep going, farther and farther, until all those galaxies blur into a delicate web, like faint silver threads against black velvet. And somewhere in this quiet drifting, a question appears. Where does this view end? There is, surprisingly, an answer. Not an edge made of a wall or a fence, but an edge made of time and light. You imagine a transparent sphere around you, centered on your current position in space. Inside that sphere, everything from which light has had enough time to reach you since the beginning of the universe. Outside it, regions that exist, but whose light has not yet arrived. That invisible boundary is what cosmologists call the observable universe. Your breathing falls into rhythm with the idea. In, light leaving distant galaxies. Out, light arriving here after billions of years of travel. Because light has a finite speed, it functions like a universal speed limit on information. The universe is about 13.8 billion years old, which might tempt you to think the radius of the observable universe should be 13.8 billion light-years. But as you float at this imaginary edge, you notice something strange. The sphere is much larger. That's because, while the light has been traveling, space itself has been stretching. The galaxies that sent their photons toward you long ago have been carried outward by cosmic expansion, like dots on the surface of an inflating balloon. By the time their light finally reaches you, those galaxies are now much farther away than the distance the light actually traveled. When cosmologists do the careful math, using measurements of the cosmic microwave background and galaxy surveys, they estimate the radius of your observable universe to be about 46 billion light-years in every direction. You let that number sink in. 46 billion light-years. A sphere so large that the brain can't really picture it, only feel around its edges with metaphors. Maybe it's like standing on a beach at night and realizing that each grain of sand under your toes corresponds to thousands of galaxies in the sky, and that the part of the cosmos you can see is just one illuminated patch in a darkness that might go on without end. At this horizon, the light you're receiving is ancient. Part of it comes from stars and galaxies as they were billions of years ago. Fainter still, underneath that, there's a whisper of much older light, the cosmic microwave background, a thin, uniform glow filling all of space. It's like the afterglow of a cosmic sunrise, light released when the universe was only about 380,000 years old, long before any stars were born. Telescopes tuned to microwaves have turned this faint radiation into a detailed map, a kind of baby picture of the universe. You imagine that baby universe as a warm fog of hydrogen and helium, glowing softly, the temperature a comfortable few thousand degrees too hot for atoms to hold onto their electrons, but cool enough that things are beginning to settle. When the fog thinned and atoms formed, light could finally move freely. Some of that light has been traveling ever since, stretched by cosmic expansion from visible and infrared wavelengths down into microwaves, like the fading echo of a once bright sound. That's what brushes against you now from every direction as the cosmic microwave background. The edge of the observable universe, then, isn't a solid shell. It's more like the farthest point in a conversation. You can only hear someone if they've had time to speak, and the sound has had time to reach you. The cosmos works the same way. You can only hear or see objects whose light has had enough time to arrive. Beyond that horizon, other galaxies could be humming along, forming stars, collapsing into black holes, drifting in their own quiet patterns. Their presence is not ruled out by physics. They are simply out of causal contact with you, at least for now. You might wonder if this horizon is permanent. Will we ever see more? In one sense, yes. As time goes on, light from slightly more distant regions will have had time to reach us, so the light travel distance increases. But the universe's expansion is also accelerating, driven by something we label dark energy. That means there's a different kind of horizon too, a future limit. Some galaxies are receding from us so fast not by moving through space, but because space itself is stretching that their light, emitted now, will never catch up. There are regions already effectively lost to us forever. It's a little like standing on a boat drifting down a wide river. The current carries you in one direction, and far upstream, someone might shout your name. But if they're too far away and the water's moving too fast, no matter how loudly they call, the sound will never reach you. Space, in this analogy, is the river itself, and dark energy is the current gradually picking up speed. Lying there in the dark, you can almost feel that subtle motion, even though everything in your room seems still. Your body, this planet, this galaxy, all of it sits inside an expanding fabric of space. The observable universe is the region from which reality has had time to introduce itself to you. Beyond that, the rest remains nameless, unlit in your personal sky. This matters for our story about parallel universes because it quietly opens the door to more. Even if there is only one grand universe in the deepest sense, the part you can observe is just a finite bubble in a possibly infinite whole. There could be regions far beyond your horizon where matter is arranged differently, where the night sky would show unfamiliar constellations, where no light from our Milky Way will ever appear. Maybe the universe just loves to hide surprises beyond each horizon. On Earth, you walk over a hill and discover a new valley. In space, you look farther and discover that even the edge you thought you saw is only the edge of your vision, not of reality itself. Tonight, as you let your eyelids grow heavier, you can hold that distinction gently. The observable universe is not the same as the entire universe. It's simply your cosmic neighborhood, defined by time, light, and the speed limit written into the laws of physics. Somewhere out there, beyond your horizon, photons are on their way toward us now, starting journeys that will outlast your life, your civilization, perhaps your species. You won't be here to see them arrive, but that's okay. Your moment is to lie here, in this small corner of space-time, and feel the quiet enormity of the part you can see a soft, glowing sphere 46 billion light-years in radius, wrapped around you like a very large, very ancient, very patient blanket of stars. You let your awareness hover at the edge of the observable universe for a moment longer, feeling that vast, invisible sphere around you. Then, gently, you rewind time. Galaxies fade, stars unform. Matter melts back into a smoother, hotter fog. The cosmic web untangles itself, like threads being pulled from a woven cloth. You keep rolling backward until the universe is unimaginably young, a fraction of a second, old, and here, in this almost beginning, something dramatic happens. You are now in a universe that is tiny, dense, and seething with energy. It doesn't look like a starry sky. It feels more like standing inside a storm cloud made of pure brightness, where there's no up or down, no here or there, just an almost uniform sea of energy. And in this storm, according to a leading idea in cosmology, space itself suddenly starts to expand at a staggering runaway rate. This episode is called Cosmic Inflation. It's not just ordinary expansion sped up. It's an exponential growth, where every tiny region of space doubles in size over unbelievably short intervals. You can imagine drawing a small dot on a balloon and then, instead of blowing slowly, you snap your breath into it so fast that the dot's neighbors race away in an instant. In inflation, the balloon is the fabric of space, and the driving force is a peculiar form of energy with strong negative pressure, often modeled as a field filling space. As this inflating space swells, something important happens to its texture. Any wrinkles, irregularities, or clumps get smoothed out, the way a rapidly stretching piece of dough evens out bumps. This helps explain why, when we look at the cosmic microwave background, that baby picture of the universe, it's almost perfectly uniform in temperature, with only tiny variations. Without inflation, different parts of the sky we see today would never have been in contact. They wouldn't have had time to agree on a common temperature. Inflation solves that puzzle by making them neighbors in the very early universe, then blowing them far apart. You can feel the strangeness of that. A single, tiny patch, stretched faster than light, not because anything is breaking the cosmic speed limit, but because space itself is expanding. That small patch becomes large enough to encompass everything you now call your observable universe. The galaxies, the stars, the atoms in your body, all once fit into something much smaller than a proton, then rode the wave of inflation outward. But inflation has another, more speculative consequence, one that directly feeds our story about parallel universes. In many models, inflation doesn't end everywhere at once. Instead, you picture space as a frothing expanse, like water near boiling. Some regions cool and exit the inflationary phase. In those regions, the energy that drove inflation decays into particles and radiation, starting something like the Big Bang as we know it. Other regions, however, keep inflating. You can imagine it as a pot of water on the stove. Bubbles form here and there, rising and popping, but the water in between is still liquid, still hot, still boiling. In the cosmic version, each bubble is a region where inflation has ended, creating a hot Big Bang universe with matter, radiation, and eventually galaxies. The inflating space between bubbles keeps stretching, spawning more space and more bubbles. This idea is called eternal inflation. In this picture, you find yourself inside one such bubble. Your entire observable universe is a tiny patch of foam on the surface of some vast, ongoing boil. Other bubbles, far beyond your horizon, would count as other universes, in a very literal sense, causally disconnected regions of space with their own histories. The texture of the energy field that drives inflation might differ slightly from bubble to bubble, which could mean that the fundamental constants of nature, or even the effective laws of physics, vary too. You float in imagination between these bubbles now. They're not actually coloured or outlined, but in your mind you tint them softly. One bubble, where gravity is a bit stronger, stars burn faster, and planets may rarely form. Another, where the charge of the electron is a little different, and chemistry never gets complex enough for life. Another where things look almost exactly like ours, down to galaxies and planets, but with tiny differences in how structure forms. You're drifting through a silent, endless foam of possible worlds, like lanterns suspended in a dark ocean. Of course, you remind yourself, this is still speculative. Inflation as a broad concept is supported by several lines of evidence. The flatness of the universe, the pattern of tiny temperature variations in the cosmic microwave background, the way structure grew from small initial seeds. But whether inflation is truly eternal, whether it really generates an infinite family of bubble universes, is not yet something we can prove. You feel the humility in that. Physicists take equations that describe the early universe, trace out their implications, and one of those implications is, this process doesn't naturally stop everywhere. The mathematics, left to itself, makes more and more inflating space, more and more bubbles. But when you ask, Can we ever see another bubble? Can we ever detect a direct imprint of one? The answers get softer, more cautious. There are ideas a collision between two bubbles might leave a faint, circular scar in the cosmic microwave background, for example, but nothing conclusive has appeared in the data so far. Lying there in the dark, you can imagine those hypothetical scars as subtle rings of slightly different temperature, like the faint outline left by a drop of water on a table. If we ever found one convincingly, it would be like seeing a fingerprint from another universe pressed lightly onto our sky. For now, the cosmic microwave background looks wonderfully consistent with a simple inflationary story where our bubble has evolved mostly on its own. Maybe the universe just loves to produce variety. On Earth, ecosystems branch into forests, deserts, oceans, each with its own rules and inhabitants, yet all obeying the same underlying chemistry. On the larger scales, perhaps reality branches into bubble universes, each an ecosystem of physics, some barren, some fertile, some short-lived, others long-lasting. You, eyes growing heavier, rest inside one such bubble, on one small planet, after one brief day, listening to theories about the unseen foam outside. Whether eternal inflation is ultimately right or wrong, the idea carries a gentle lesson. Even the most successful scientific theories are not final stories, but works in progress. They start close to the data, the sky. The particles then lean out into the unknown, extending their logic as far as it will go. Some extensions will turn out to be too bold. Others may be confirmed by future observations. Tonight, you don't have to choose a side. You can simply float between the bubbles in your mind, feeling how large the stage of reality could be, and how precious it makes this one glowing bubble that currently cradles you to sleep. You leave the bubbling foam of universes behind and begin to fall inward, as if someone has turned a cosmic zoom wheel. The clusters of galaxies shrink to single points. Galaxies collapse into stars, stars into atoms, atoms into smaller and stranger things. The world around you stops looking like a smooth fabric and starts looking grainy, jittery, as if reality itself is made of tiny, restless questions. You drift down to the scale where quantum mechanics rules. Here, particles aren't little marbles with clear positions and paths. Instead, they behave more like ripples on a pond of possibility. You feel the air in your room as a soft mist on your skin, yet in this new view, that mist is made from atoms whose electrons do not orbit like planets in miniature. They exist in smeared-out clouds, described not by certainties but by probabilities. You find yourself standing just in imagination at a famous experiment, the double slit. A beam of electrons, or photons, is heading toward a barrier with two narrow openings. On the other side is a screen that records where they land. Classically, you'd expect each particle to go through one slit or the other, like tiny bullets. But when you let them through, one by one, a delicate pattern gradually forms on the screen. Bright and dark bands, an interference pattern, the kind you'd see if waves of water were passing through both slits and overlapping. You can almost hear it. A gentle hush of invisible waves arriving at the screen, crest meeting trough, reinforcing here, cancelling there. Yet when you look closely at the detections, they appear as single, sharp dots. Each electron lands at one place, as if it were a discrete little thing. Wave and particle, spread out possibility and localized impact, coexist in this quiet experiment. Now you place detectors at the slits, trying to catch each electron in the act, to see which path it takes. And something eerie happens. When you measure which slit each electron goes through, the interference pattern dissolves. The particles behave more classically, as if they've been forced to choose. The universe seems to react to your decision to look. You float in that strangeness for a moment, feeling how it nudges against common sense. In ordinary life, a ball doesn't take both routes to the goal until someone watches. A cat doesn't hover between asleep and awake. Yet the equations of quantum mechanics describe systems as superpositions, mixtures of many possible states at once, until they are measured. This is where interpretations come in, whispering different stories about what the mathematics really means. The equations themselves are widely agreed on. They make predictions that match experiments to astonishing precision. But when you ask, softly, what is actually happening underneath, the answers fork like paths in a forest. One answer, taught in many textbooks, says that the wave function, the mathematical object that encodes all those possibilities, collapses when you make a measurement. Before you look, the electron's position is spread out like a cloud of maybe here, maybe there. When you observe it, that cloud instantaneously shrinks to a single outcome. The universe picks one result, and the others simply do not happen. This view is pragmatic and works beautifully for calculations, but it leaves puzzles. What counts as a measurement? Why should the equations change their form just because a conscious observer appears? Another answer is quieter but more radical. Maybe nothing ever collapses. This is the many worlds interpretation. You let the idea unfold in your mind, like a slow, surprising flower. In many worlds, the wave function never jumps. It evolves smoothly and deterministically, all the time, according to the same equation. When you perform a measurement, you and the system become entangled. You don't force the universe to choose one outcome. Instead, the universe splits into branches, and each possible outcome is realized in a different branch. In one branch, you see the electron land in a bright stripe on the screen. In another branch, you sees it land in a dark gap. In yet another, it lands somewhere else. You never feel the split, because each version of you remembers only the outcome in their own branch. It's like a book that keeps writing new chapters, each chapter following some but not all of the earlier plot lines, and each reader only ever sees one continuous story. To make this less mystical, quantum physicists talk about decoherence. You picture a fragile quantum system, say, a tiny particle in a superposition of two locations, like a soft chord on a guitar string, vibrating in two notes at once. As soon as it interacts with the environment, air molecules, stray photons, your measuring device, the information about its state leaks out, gets spread into countless other degrees of freedom. The delicate chord blurs into noise. The different branches of the wave function, corresponding to different outcomes, stop interfering with each other. For all practical purposes, they behave like separate, non-communicating histories. You imagine dust floating in a sunbeam. Initially, the specks form one smooth, streaming pattern. Then a soft breeze passes through, and the dust splits into different currents, each drifting its own way. The air molecules are like the environment in decoherence. Once they've nudged the dust into different paths, those paths don't recombine. Likewise, in many worlds, once branches have decohered, they don't interact again. Each is a self-contained narrative. The remarkable thing is that many worlds does not introduce new equations or new forces. It takes the standard quantum rules, removes the special collapse postulate, and says, let the math be universal. Let it apply to measuring devices and people too. The price you pay is conceptual. You must accept that reality might be vastly bigger than what any one observer can see, a sprawling tree of branching histories, all realized. You lie there with that thought, feeling its weight, but also its odd calm. In a sense, many worlds makes the quantum world less random. Everything that can happen does happen in some branch. The randomness you feel is like waking up in one page of a choose-your-own-adventure book without access to the others. Yet there's no way, as far as we know, to hop between these branches or send messages across them. They're parallel not in space, but in the structure of the wave function. Is it true? No one knows for sure. Many worlds fits the math and ordinary experiments just as well as the collapse picture. It gains points for internal elegance, loses points, in some people's eyes, for multiplying realities beyond what we can observe. Other interpretations exist too, pilot wave theories where hidden variables steer particles, relational views where properties exist only relative to other systems. Each one tries to turn the bare equations into a story about what is. Maybe the universe just loves to give you choices, not only in your daily life, but in how you imagine its foundations. You can be the kind of person who finds comfort in a single, collapsing world, where possibilities evaporate the moment an outcome appears. Or you can lean into the idea that every quantum event is a branching, that the cosmos is richer and stranger than any single slice can show. Or you can simply let the question remain open, like a softly glowing doorway at the end of a hallway not yet entered. As your thoughts slow, you bring your awareness back to something small and tangible, a single atom in the air above your pillow. Its electrons described by a quantum wave function that has been evolving calmly for billions of years, through stars and space and time, before finding its way here. Whether that wave function collapses or branches into many worlds, it still helps shape the breath you take, the neuron that fires, the dream that begins. You linger for a while among the quantum possibilities, like someone standing at the trunk of a great tree, watching the branches spread out into the dark. Many worlds, decoherence, wave functions that never quite collapse. These are big, abstract ideas. Tonight, you bring them closer. You want to feel, at least in imagination, how a world might actually split, not in equations on a chalkboard, but in the quiet details of an ordinary moment. So you start small. You picture a single particle, say, an electron on a lab bench somewhere. The room is dim, the air cool, the only sound a soft hum from the equipment. In this scene, the electron is prepared in a superposition of two locations, left and right. Quantum mechanics says it isn't just undecided. It genuinely occupies a state that is left and right at the same time, as far as the math is concerned. You let that sink in by turning it into an image. You see two faint, overlapping glows in the air, one on the left, one on the right. The electron is not a tiny bead hiding in one of them. The electron is the entire pattern. Both glows together. That's the initial state. Next, you add a measuring device, a detector that can light up if the electron passes through its region. Maybe it's a little screen with 2 pixels, 1 pixel on the left, 1 on the right. Left pixel corresponds to electron on the left, right pixel to electron on the right. Before the measurement, the detector is in a neutral state, both pixels off. Now, you gently let the electron and detector interact. The laws of quantum mechanics say the combined system electron plus detector evolves smoothly. The superposition doesn't vanish, it spreads. After the interaction, the electron left part of the wave function becomes entangled with the detector left on state, and the electron right part becomes entangled with the detector right on state. In your mind's eye, the scene looks like this. In one branch of the wave function, the left glow brightens, and the left pixel flicks on with a soft click and a tiny warmth you could feel if you touched it. In another branch, the right glow brightens, and the right pixel clicks instead. Both branches are there in the math, coexisting, contained in a single giant wave function. At this stage, you haven't split the world yet, not in the full sense. You've created a fragile quantum correlation. The system is still delicately balanced, like a chord played on 2 strings at once. If you could somehow isolate everything perfectly, you might even make those branches interfere again and erase the record of which pixel turned on. But you can't isolate everything. The detector is warm. It's bumping into air molecules, exchanging photons with the environment, vibrating ever so slightly. The moment one pixel lights up, it emits light. It heats a tiny bit. It shoves against the surrounding atoms in a way that's ever so slightly different from what would happen if the other pixel had lit instead. This is where decoherence quietly walks onto the stage. Every extra interaction with the environment, each scattered photon, each jostled air molecule, carries away a little bit of information about which pixel fired. That information becomes embedded in countless degrees of freedom around the device, spreading outward like ripples on a pond. The 2 branches of the wave function, left click and right click, start to lose their ability to interfere with each other, because each is now entangled with a vast and different web of environmental states. You imagine that web as dust motes drifting in a sunbeam above the detector. In the left-click branch, the dust motes trace one set of subtle patterns. In the right-click branch, they trace a slightly different set. You'll never track those differences in detail, they're too fine, too numerous, but at the level of the wave function, they are very real. They push the branches apart, not in space, but in the space of possibilities. Now, add yourself to the picture. You walk into the lab, your footsteps muffled by the floor, the smell of metal and coffee lingering in the air. You look at the detector to see which pixel is on, but by the time your eyes arrive, the wave function has already spread further. Electron entangled with detector, detector entangled with environment, environment entangled with you. In one branch, your retina absorbs photons from the glowing left pixel. In another branch, from the right pixel. The light triggers slightly different patterns of nerve signals, which travel along your optic nerve and bloom into different brain states. In one branch, you have the conscious experience. Ah, it's left. In the other, ah, it's right. You don't feel any splitting. You simply find yourself with a definite memory. The world, as experienced from within a branch, never feels like a superposition. It feels crisp, either left or right, either this or that. From the outside, from the imaginary vantage point of the full wave function, there was no moment when a single outcome was chosen. There was only gradual entanglement, spreading correlations, and decoherence, making the branches dynamically independent. The split, in many worlds' language, is not a sharp, magical event. It's a continuous process where quantum possibilities become embedded in different patterns of the environment until interference between them is effectively impossible. You can apply the same logic to something closer to your own life. Picture a simple quantum event inside a computer chip that controls a random number generator. That chip decides whether to send you a message, maybe a playful text, maybe a small notification. The chip's random decision depends on a quantum process, say, the decay of an atom or the detection of a photon. In one branch of the wave function, the quantum event goes one way. The bit flips to 0, no message is sent. In another, it goes the other way. The bit flips to 1, and a message appears. That message changes your evening just a little. Maybe it distracts you for a few minutes, shifts your mood, nudges you to reply, leads to a different conversation, a different choice about when you go to bed. Over time, those ripples compound. From your point of view inside one branch, life feels continuous and singular. You either got a message or you didn't. But viewed through the many worlds lens, there are now two macroscopic histories, each containing a version of you with a slightly different chain of events behind them. As decoherence piles up, those histories diverge more and more. After a while, there's no practical way to say they're just small quantum differences. They're separate worlds, each internally consistent, each containing people who feel as real and unique as you do right now. You might worry that this makes everything feel less meaningful, as if your choices are diluted across too many branches. But consider a softer perspective. In each branch, you still experience uncertainty before you look. You still feel the weight of decisions. You still care about outcomes. Your moral responsibilities, your emotions, your stories all live inside the branch you actually inhabit. The existence of other branches doesn't cancel that. It just means that the underlying reality may be deeper and more redundant than your mind can hold at once. Maybe the universe just loves to recycle possibility, never wasting a quantum option, letting every allowed path unfold somewhere in its vast wave function. Your job is not to manage the branches. Your job is simply to live well in the one you perceive, to treat the people you meet as singular and precious, even if a mathematician might say there are countless versions of them in other, forever unreachable histories. As you let this sink in, you bring your attention gently back to your own body. Right now, decoherence is happening all around you, and inside you, molecules collide in the air you breathe. Photons bounce off the walls. Neurons fire, interacting with trillions of other degrees of freedom. The quantum state of the universe is branching and branching. Yet what you feel is a single, continuous thread of experience, like a soft line being drawn across a page. You don't hear the splits. You don't see them. You fall asleep inside one branch, and you wake up inside that same branch tomorrow with memories that connect yesterday's you to today's. The physics underneath may be wild and branching, but the story you live remains, mercifully, one chapter at a time. You rise slowly from the quantum lab bench, leaving behind the tiny clicks of detectors and the ghostly branching of wave functions. The scene pulls back again, but this time, instead of returning straight to galaxies and cosmic foam, you stop in a different kind of space. A space made not of stars, but of equations. Here, another bold attempt to understand reality is waiting for you, string theory, with its hidden dimensions and shimmering brains. You imagine the ordinary particles you've heard of: electrons, quarks, photons as small beads, tiny dots in the fabric of the universe. That's how standard quantum field theory treats them, point-like, with no internal structure. But in string theory, you gently swap that image out. Each particle becomes a tiny vibrating string, like an impossibly small violin string under unimaginable tension. Different vibrational patterns correspond to different particles. Pluck it one way, and you get an electron. Another way, and you get a photon. Another way, and you get the graviton, the hypothetical quantum of gravity. You let your mind's ear listen to this microscopic orchestra. Every point in space around you, above your pillow, inside your chest, beneath the floor, is filled with strings singing silently in dimensions too small for your senses. The air you inhale becomes a symphony of threads, each vibration encoding a property: mass, charge, spin. But to make the mathematics of these strings consistent, something surprising happens. The equations don't quite work in a universe with only 3 dimensions of space and 1 of time. They insist on more room, extra spatial dimensions beyond the length, width, and height you know so well. Superstring theories typically need 10 dimensions in total. Their cousin, M theory, suggests 11. The extra ones aren't sprawling, open directions like the usual 3. Instead, they are curled up, compact, wrapped into intricate shapes at every point in space. To picture this, you imagine a garden hose in the dark. From far away, it looks like a simple line, one-dimensional. But if you get close enough, you see it has thickness. You can walk around it, not just along it. The hose has extra dimensions that were invisible from a distance. In string theory, each point in ordinary space hides a tiny hose, or something far more elaborate, like a many-holed surface called a Calabi-Yau manifold. Strings can vibrate not just along the large dimensions, but also around and within these curled-up spaces. The shape of the extra dimensions influences which vibrations are allowed, and therefore which particles exist and what their properties are. You drift closer to one of these tiny hidden shapes, shrinking in imagination until you're small enough to see it. It looks like a delicate crystal cathedral, all smooth curves and tunnels and folded surfaces, lit from within by the faint glow of string vibrations. Each possible path the string can wind around is another note in the grand cosmic chord that becomes physics in our familiar 4 dimensions. Then another ingredient appears: brains. In string theory, strings can be closed loops, like rubber bands, or open segments with endpoints. Those endpoints are not allowed to just end in empty space. They must attach to higher dimensional objects called D-brains. A brain is like a sheet or membrane, but it can have many dimensions, not just 2 like a rubber sheet, but 3, 4, or more. You can imagine a 2-dimensional brain as a flat surface, a 3-brain as a kind of volume-filling block, and so on. Now, picture our entire visible universe as a 3-dimensional brain, a 3-brain floating in a higher dimensional bulk. All the familiar particles of the standard model, the ones made from open strings whose ends are tied to our brain, are stuck to it. They can move left, right, up, down, forward, backward within the brain, but not off of it. Gravity, however, associated with closed strings that form loops, can roam more freely through the extra dimensions. That difference might explain why gravity feels so much weaker than the other forces. Its influence is diluted by spreading into the higher dimensional bulk. You stand on this brain universe now, feeling the floor under your feet as part of a vast, invisible sheet. All the matter you know, stars, planets, trees, cats, you are ripples and knots on this sheet. Above and below it, in directions you can't point to with your finger, stretch extra dimensions, perhaps with other brains floating in them, like parallel pages in a book you cannot open. The higher dimensional bulk is quiet, dark, thin as a whisper against your skin. In some scenarios, these extra dimensions may be compact, but relatively large compared to the Planck scale, curled up into loops that might, in principle, leave traces in high-energy experiments or gravitational measurements. In others, like the warp geometries of Randall-Sundrum models, space can be curved so strongly that distances along the extra dimension don't behave the way your intuition expects. The picture becomes one of steep gravitational wells and cliffs, reshaping how gravity spreads between brains. You can feel that curvature as a kind of tilt under your feet, a gentle slope in the invisible bulk. If another brain lives across that slope, its physics might look different. The strengths of forces, the masses of particles, the behavior of gravity all could vary from brain to brain, depending on how they're placed in the higher dimensional landscape and how the extra dimensions are shaped and warped. This is where the idea of a string landscape begins to flicker into view. String theory doesn't seem to give you just one way to curl up the extra dimensions and arrange the brains. It gives you an enormous menu, possibly something like 500 distinct, metastable configurations, each with its own effective laws of physics. Most of them might be sterile or inhospitable, but a few could produce universes where stars form, chemistry flourishes, and minds wonder about their origins. You imagine walking through that landscape as if it were a vast, mountainous country at dusk. Each valley corresponds to one particular way the extra dimensions are curled, one particular arrangement of brains, one particular set of constants and forces in the lower dimensional world perceived by any inhabitants. From the bottom of a valley, all you see is your own sky, your own physics. You might never suspect that other valleys exist at all. It is easy to turn this into a story of many universes. Each valley, each brain world, each compactification becomes its own cosmos, with its own version of what's possible. But tonight, you keep a gentle distance. You remember that string theory is still a work in progress, mathematically rich, but experimentally unconfirmed. Extra dimensions and brains are beautiful ideas that might describe reality, or might be a stepping stone towards some deeper framework we haven't discovered yet. Still, you can let the imagery soothe you. The notion that your familiar 3 dimensions might be just a slice of a larger structure gives your room a secret depth. The wall behind your bed, the ceiling above you, the phone in your hand all become part of a higher dimensional architecture, like decorations on a vast, unseen stage. Maybe the universe just loves to hide its complexity in folds and curls. On a leaf, patterns of veins hide inside the simple outline. In DNA, oceans of information hide in a microscopic helix. In string theory, entire worlds might hide in dimensions rolled up so tightly that no beam of light has yet teased them open. As your breathing slows, you don't need to decide whether strings and brains are correct. You can simply lie here, feeling the softness of your pillow, while somewhere in the minds of theorists, chalk traces the shapes of extra dimensions on blackboards, and equations weave possible universes together like threads in a cosmic tapestry. If some of those threads correspond to other brain worlds, other valley universes, they are, for now, part of a quiet mathematical dream, one you're allowed to borrow as a bedtime story before you drift further into the dark. You float now between ideas. Inflation's bubbles on one side, string theory's landscape of valleys and brain worlds on the other. Somewhere between them lies a quieter, more intimate question, one that sneaks into your thoughts like a whisper. Why do the numbers of nature have the values they do? You open your eyes. Just in your mind, inside this universe's control room. It's not a real place, of course, but it feels like it. A dimly lit chamber with a circular console, dotted with glowing dials. Each dial controls one of the fundamental constants. Over here is the strength of gravity. Over there, the strength of the electromagnetic force. Another dial sets the mass of the electron. Another the strength of the strong nuclear force that holds atomic nuclei together. Another the cosmological constant that drives the acceleration of cosmic expansion. Right now, in your universe, all these dials are set to very particular positions. You run your fingers lightly over them, feeling the faint warmth of their glow. You don't know why they're set this way. You only know what happens because they are. Atoms are stable. Stars can shine for billions of years. Carbon, oxygen, and heavier elements can form in stellar furnaces. Planets can orbit quietly in the habitable zones of stars. Chemistry can become complex enough for cells, brains, and late-night videos about parallel universes. Now, gently, you imagine nudging one dial. Not all the way to 0, not to something wildly different, just a little. Make gravity slightly stronger. The pull between masses increases. Stars might burn hotter and faster, collapsing sooner. Massive stars could collapse into black holes before they've had time to seed the cosmos with heavy elements. Galaxies might form differently. Perhaps the universe clumps up too quickly, losing the long, gentle eras where life could evolve on stable worlds. Slide gravity the other way, a little weaker. Now matter clumps more slowly. Maybe stars take much longer to ignite, or galaxies never form as richly. Instead of bright spiral cities of stars, you might get a sparse, dim universe where hydrogen and helium drift almost forever without ever settling into the long-lived, steady stars that life seems to prefer. You turn to another dial, the strength of the strong nuclear force. This controls how tightly protons and neutrons bind inside atomic nuclei. Turn it up, and nuclei cling too fiercely. Almost all protons and neutrons might fuse into heavy elements, leaving no hydrogen to fuel stars or to form water. Turn it down, and nuclei fall apart too easily. Only hydrogen remains, and complex chemistry stalls before it starts. In the space of possible settings, the range that permits a rich periodic table, and thus the chemistry of life as we know it, might be surprisingly narrow. Then there is the cosmological constant, or dark energy density, the dial that sets how quickly the expansion of the universe accelerates. If it were much larger and positive, space would fly apart so fast that matter would never gather into galaxies. Everything would thin out into a lonely, nearly featureless fog. If it were large and negative, the universe might recollapse long before stars and planets had a chance to form. Our actual value seems incredibly small compared to the natural scales suggested by quantum field theory. It's as if this dial is tuned to a setting like 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 instead of something closer to 1, and no one really understands why. You stand in this imaginary control room, looking at all these dials, and a feeling settles over you. Improbability. Not in the strict, calculable sense. We don't know the true space of possible universes well enough to assign precise probabilities, but in a softer, intuitive sense. It's as if everything about this room is arranged just so, in a way that allows you, a thinking observer, to be here at all. This sense is what people mean by fine-tuning. The term doesn't claim certainty that the universe is finely adjusted with conscious intent. It simply notes that small changes in certain constants within the framework of our current models tend to wipe out the conditions needed for complex structures like stars, planets, and life. That pattern is striking enough that many physicists and philosophers have paused to ask what to make of it. You breathe out slowly, feeling both the awe and the discomfort of that observation. One response is to say, we shouldn't be surprised. We can only find ourselves in a universe compatible with our existence. This is the anthropic principle, stated in its modest form. Out of all possible regions of a multiverse, you inevitably wake up in one where the dials permit your kind of life. If there is a vast ensemble of universes, eternal inflations, bubbles, string theories, landscape, or something else, then rare friendly settings might be inevitable somewhere, and observers will only ever report from those. In this view, you're like a person waking up on a planet with breathable air and liquid water. You could marvel at the coincidence. What are the odds I landed on a life-friendly world? But if there are countless planets, and you can only exist on ones that support life, then your surprise fades. It's still special, still beautiful, but perhaps not suspicious. Another response, from some physicists and philosophers, is to treat fine-tuning as a clue that our theories are incomplete. Maybe the constants we treat as arbitrary inputs will eventually be derived from deeper principles. Perhaps a future theory will show that only a narrow range of values is mathematically self-consistent, or that things we thought were independent are in fact linked. In that case, what seems finely tuned today might, tomorrow, be revealed as inevitable. You don't have to choose tonight which of these attitudes is right. You can sit with the question itself. You lie there, feeling the gentle tug of Earth's gravity on your body, that same gravity whose strength seems just right for stars and planets and stable orbits. You feel the subtle warmth in your skin, energy transferred from photons that began in the heart of the sun, thanks to nuclear reactions balanced precisely by the strengths of the strong and electromagnetic forces. Maybe the universe just loves to make unlikely things commonplace. Snowflakes, each unique, yet all following simple rules of crystallization. Life, rare in the vastness of space, but ordinary on a living planet. A universe that looks finely tuned from one angle might be the natural generic outcome from another angle you haven't discovered yet. Still, the idea of a cosmic lottery lingers. If there is a multiverse, a huge ensemble of universes with different dials set to different values, then you can imagine a vast ticket drum spinning in the darkness. Most tickets correspond to universes with no galaxies, or short-lived stars, or sterile chemistry. A tiny fraction correspond to universes like yours, where complexity and consciousness can arise. You hold one of those rare tickets. You know that because you're here to notice anything at all. You don't have to turn that into ego or despair. It can become a kind of quiet gratitude. In this branch, with these constants, after these 13.8 billion years, you find yourself lying in bed, listening to a story about parallel universes and fine-tuned dials. You are a brief, local pattern inside a universe that, for reasons not yet fully known, allows patterns like you to bloom. As your eyelids grow heavier, the control room fades. The dials dim to embers, then to darkness. What remains is the feeling that the laws of physics are not just background rules, they are part of the story of why you're here at all. Whether that story is one of lottery and selection, deep necessity, or some mixture of both is an open question, one that the universe invites you to ponder for a while, and then gently set aside as you drift towards sleep under finely balanced stars. The dials of the cosmic control room fade, and in their place you find something much simpler: darkness. Not empty, frightening darkness, but the kind of deep night you see when you look up from a countryside field far from city lights. A velvet black, punctured by a few pinpoints of stars. As your eyes adjust inside this imagined sky, one patch of darkness looks different. A region where even the starlight seems to disappear, as if the night itself has taken a deeper breath. You're looking at a black hole. You drift closer, carried on a quiet current of thought. Near the black hole, the stars behind it distort and swirl, their light bent by gravity into arcs and rings. You can almost feel the pull, not as a physical tug on your body, but as a slow, insistent leaning in your attention. Your mind wants to understand what happens here, where gravity, time, and space all push themselves to an extreme. A black hole begins with something very bright, a massive star, much larger than the Sunday. It burns through its nuclear fuel, fusing lighter elements into heavier ones, fighting a constant war between outward pressure and inward gravity. Eventually, the fuel runs out, the pressure drops, gravity wins. The core collapses. If the star is massive enough, no known force can halt the collapse, and the matter falls inward until it forms a region so dense that the escape velocity exceeds the speed of light. You picture escape velocity like this. On Earth, you'd need to throw a ball at about 11 kilometers per second to send it out of Earth's gravitational grip forever. Near a black hole, the necessary speed rises and rises. At a particular boundary, the event horizon, that speed reaches the speed of light. Since nothing can outrun light, nothing that crosses this surface ever comes back out. Not light, not particles, not signals. From the outside, the event horizon is a one-way veil. You hover just outside that invisible boundary. Time behaves strangely here. If you watch a clock falling toward the horizon, its ticks slow down, redshifted and stretched, until from your point of view they almost freeze. To the falling clock itself, nothing special seems to happen at the horizon. It simply continues inward, though what awaits it deeper inside is something our current theories struggle to describe. The curvature of space-time near the black hole is so intense that the usual concept of inside and outside of space and time starts to blur. In the classic solutions of Einstein's equations, the region inside the event horizon is not just a deeper pocket of space, it's a different kind of region entirely, where the direction toward the center behaves more like time than space. Once you cross the horizon, moving toward the singularity, the place where the equations predict infinite curvature and density, is as inevitable as moving from tomorrow into the day after. You don't follow the clock all the way in. You pause, suspended at the brink, and let a different idea rise. Mathematically, the simplest eternal black hole solutions don't just contain an event horizon and a singularity. They also contain other regions of space-time, connected in strange ways, bridges known as Einstein, Rosen bridges, or wormholes, which in their idealized form link two separate universes or distant parts of the same universe. In reality, such bridges are thought to pinch off too quickly to travel through, but their existence in the equations hints that the interior of a black hole could be more than a dead end. This is where the notion of baby universes appears, soft and speculative. Some physicists have wondered, what if the collapse of matter inside a black hole doesn't end in a true singularity? What if, when quantum gravitational effects become important deep inside, the collapse bounces instead? In that bounce, space-time could re-expand, not back into our universe, but into a new, separate region, a baby universe budding off from its parent. You imagine the black hole not as a simple pit, but as a seed. From the outside, it still looks like a dark, spherical boundary in our universe, shrinking slightly over time as it emits Hawking radiation and evaporates. But inside, Beyond what any external observer can see, space might be unfolding again, like a new Big Bang in a hidden room. This interior expansion could stretch out into its own cosmos, with its own arrow of time, its own galaxies, maybe its own life. The event horizon in our universe would then be, in some sense, the umbilical cord through which that baby universe was born, now sealed off. A more structured version of this idea is called cosmological natural selection, proposed by physicist Lee Smolin. In that picture, universes give rise to new universes through black holes. The laws of physics, or at least certain parameters, might change slightly with each generation, like mutations. Universes that make more black holes have more offspring, so over cosmic time, universes that are good at forming long-lived stars, which can collapse into black holes, become more common. It's a wild notion. Black holes as reproductive organs of the cosmos. You drift along a tree of universes, each one sprouting black hole buds, each bud potentially blooming into a new expanding space. The whole structure looks, in your mind, like a glowing mycelium of reality, branches upon branches, each node a universe, each thin thread a black hole connecting parent to child. Deep within one branch, you see your own universe, a 13.8 billion-year-old bubble, filled with galaxies, where some of those galaxies have grown central supermassive black holes of millions or billions of solar masses. Each of those might be, in this story, the cradle of another universe. Of course, you remind yourself gently, we do not yet have evidence that this happens. Our understanding of black holes is still incomplete, especially at their cores, where classical general relativity predicts singularities and quantum gravity must take over. We know that real black holes form from collapsing stars, and that they curve spacetime so strongly that an event horizon forms. We have observed their effects on nearby matter and light, and even imaged the shadow of a supermassive black hole against glowing gas. We have detected the gravitational waves from black hole mergers ringing through spacetime, but what happens beyond their horizons is hidden from us, and may always be. You let that unknowability be part of the bedtime atmosphere. Maybe baby universes are real, and every black hole is the hushed beginning of an unseen cosmos. Maybe they are not, and black holes simply represent extreme, terminal states of matter and space-time in this universe alone. Either way, they remind you that the laws of physics, pushed to their limits, can lead to possibilities that our everyday intuition never needed. Think of how often endings become beginnings in the cosmos. A star dies in a supernova and scatters heavy elements into space, which later condense into new stars, planets, and eventually the atoms in your body. A galaxy collides with another and, in the chaos, triggers bursts of star formation. Even in your own life, the closing of one chapter often makes room for the next. The baby universe idea takes that pattern and lifts it to the highest level. Perhaps even the death of matter into a black hole might be, from another perspective, the birth of a new universe. Maybe the universe just loves recycling, turning collapse into expansion, darkness into new light, over and over again on scales you can barely imagine. Lying there, you can feel both the wildness and the calm of this picture. Black holes are out there, scattered through our galaxy and others, but they are far, far away from you, doing their intense, quiet work in distant corners of the sky. They do not threaten your bed, your room, your planet. Instead, they sit at the edges of understanding, pulling on human curiosity the way they pull on light. You can close your eyes and imagine that somewhere, inside one of those silent dark spheres, a new universe is swelling, its own stars just beginning to form, maybe one day, giving rise to minds that will look up at their sky and wonder how their cosmos began. They will not see you, and you will not see them. Yet in this speculative story, you are distant cousins, joined by a hidden, gravitational family tree. As sleep edges closer, you don't need to know whether that tree really exists. It's enough to feel that the laws we do know, gravity, relativity, quantum mechanics, already tie endings and beginnings together in beautiful ways. Black holes, baby universes or not, are reminders that reality has layers, and that somewhere beyond your last waking thought, space and time are still bending and flowing in ways that hint at stories the universe has not yet fully told. You find yourself back in your room again, for a moment. The glow of your screen, the soft rectangle of light on your hands, the faint hum of whatever device you're using to listen. Outside, maybe a street lamp spills a cone of yellow onto the sidewalk, rain damp or dusty. Everything feels ordinary, physical, solid. Then you tilt your attention just a little, as if looking at the world out of the corner of your eye, and another possibility slips in. What if this is all being rendered, not in a dramatic, movie way with green code raining down the walls, but in a quieter, more abstract sense? What if the fundamental reality lies somewhere else, and what you experience this world, this body, this sky, is part of a vast, detailed simulation? The idea is old in spirit. Philosophers have long asked how you can ever be sure that what you perceive is real. You imagine Plato's prisoners in the cave, seeing only shadows on the wall. Descartes worrying that an evil demon is feeding him a fake world, the brain in a vat thought experiments, where all your sensations are just signals sent to an isolated brain. The modern twist is that, instead of demons or gods, we picture computers. In one careful modern version, the simulation idea isn't just a wild guess. It's framed as a structured argument. You picture a far future civilization, unimaginably advanced compared to us. Its computers are not clunky boxes on desks, but perhaps planet-sized networks, or finely structured quantum machines. Such a civilization, in principle, might have the power to simulate entire worlds, histories as rich and detailed as ours, populated by beings like you, whose thoughts and feelings emerge from patterns of computation. The philosopher Nick Bostrom turns this into a trilemma: three options, at least one of which, he argues, must be true. Very roughly, they go like this. First, almost no civilization like ours ever reaches that technologically godlike stage. They wipe themselves out or stall before then. Second, some do reach it, but they choose not to run. Ancestor simulations, detailed simulations of conscious beings with histories like ours, for ethical, practical, or other reasons. Third, if many such simulations are run, then simulated beings would vastly outnumber beings living in base-level reality. And in that case, a randomly chosen conscious observer is overwhelmingly likely to be simulated rather than original. You let that logic echo in your mind. It isn't claiming, we are in a simulation. It's saying, if advanced simulations are common, then statistically we probably are. If we're not, then one of the other two options must be true instead. The argument is less about computers and more about probabilities and self-location. It's like waking up in a hotel corridor lined with identical doors and being told that 99 out of 100 rooms contain VR pods with simulated guests, and only one room has a real guest. If you have no other information, it's rational in that narrow sense to suspect you're probably one of the simulations. You imagine the universe as a vast, quiet server room now. Racks and racks of unseen hardware, fans whispering, tiny indicator lights blinking in colored rows. Inside that hardware, your cosmos runs. Galaxies rendered when needed. Microphysics calculated only where the simulation requires fine detail, like textures in a video game popping into high resolution near the player and blurring in the distance. It's a strangely comforting image. In a way, someone, somewhere, cares enough to run this. But then another thought comes. Even if the simulation argument is logically coherent, that doesn't mean it's true. Each step of the trilemma depends on assumptions. Are conscious beings even possible as purely computational patterns? Does physics allow such simulations at the required fidelity? Would posthuman civilizations choose to run them, and in what numbers? Some philosophers and physicists push back, arguing that we have no reason to be confident about any of that. Others point out that the simulation hypothesis is hard to test. A good simulation, by definition, would be designed so that it feels like a consistent universe to its inhabitants. Any glitches, oddities in physics, strange coincidences, could just as easily be features of base reality as clues of a simulation. Proposals to detect lattice-like artifacts in the behavior of particles or limits in the precision of physical laws that might betray an underlying grid are clever, but so far none has produced convincing evidence either way. You might hear people talk about escaping the simulation or breaking it, but those ideas are best treated as story fuel, not as real plans. Even if you did live in a simulation, the only physics you have access to is the physics of the simulation. trying to overflow the memory of the universe by overcomplicating experiments, or to send messages to the outside by staging dramatic events, is more like role-playing than genuine engineering. At our current level of knowledge, the simulation hypothesis sits at the edge of science, shading into metaphysics, not obviously false, not clearly testable, hovering in that uneasy in-between. You close your eyes and pay attention to something simple, the sensation of your breathing, air in, air out, the weight of your body on the bed or chair, the feeling of fabric against your skin. Whether these experiences are grounded in some fundamental substrate of particles and fields, or in patterns of information spinning in a cosmic computer, they feel the same from the inside. Pain hurts, joy warms, curiosity flickers, regardless of the hardware. This leads to an important thought. If the simulation hypothesis were true, would it actually change what matters? One line of reasoning, explored by philosophers, says that if the simulated world is stable, lawful, and rich enough to support creatures like you, then it is real enough for meaning. A simulated tree can still give simulated shade. A simulated kindness can still comfort a simulated mind that truly feels. The word simulated may sound like fake, but from the first-person perspective, reality is simply whatever consistent world your experiences plug into. Of course, there are unsettling possibilities too. If someone is running the simulation, do they ever intervene? Could they pause, rewind, or reboot? Are there ethical obligations toward simulated beings? Those questions extend our moral circle in a strange new direction, beyond animals and future AIs, to perhaps including beings whose existence depends on some distant programmer not flipping a switch. Some thinkers argue that if we ever gain the power to create conscious simulations ourselves, we will inherit those responsibilities well, become simulators in our own right, and the line between real and simulated will blur even more. But tonight, you can step back from that vertigo. Whether or not this universe is simulated, its patterns are elegant enough, its laws stable enough, that stars form, planets coalesce, chemistry dances, and late at night, you can listen to stories about worlds beyond worlds. The simulation hypothesis, in some sense, is just another way of saying, maybe what you see is only a surface, and underneath is a deeper level of structure. Quantum fields, strings, and brains, bubble universes, or some giant cosmic processor. Each of these ideas differs in detail, but they all echo the same intuition. There is more to reality than appears at first glance. Maybe the universe just loves mirrors. Plato's cave, Descartes' demon, brains in vats, digital simulations, each one reflects your own doubt back at you, asking what you really know and how you know it. Instead of letting that doubt paralyze you, you can let it soften your certainties, make you kinder to other perspectives, more open to surprise. As your thoughts start to slow, you look once more, in your imagination, at your room from a distance, the small rectangle of light, the quiet shape of your body, the gentle rise and fall of your breath. If this is a simulation, it is a remarkably detailed one, and the simplest thing you can do inside it is still the most profound. To be present for your own experience, to care about others who share this world with you, and to let wonder coexist with not knowing. You don't need to decide tonight whether you're made of atoms in base reality or bits in some higher-level machine. You only need to feel the mystery of being anything at all, a conscious point of view in a vast structure, whatever lies underneath. That mystery is real, simulation or not, and it's more than enough to accompany you gently towards sleep. You lie there, surrounded by the quiet of your own universe, the faint electromagnetic hum of your devices, the soft pull of Earth's gravity, the invisible sea of cosmic microwave background photons drifting through your body. For all the talk of multiverses and many worlds, everything you actually feel is perfectly local. Your bedsheet, your heartbeat, your breath, and still, that question glows gently in the dark. If there are other universes, can they ever touch this one? You start with the inflationary bubbles. In that picture, you remember, space is like a boiling pot, with bubbles of normal space universes like ours forming inside a larger inflating background. Bubbles can, in principle, appear near each other. If they do, their walls expand outward at nearly the speed of light. You imagine two such bubbles growing in the same vast darkness, like two soap bubbles blown toward each other on a cold night. As they expand, their walls eventually collide. You picture the impact as a gentle but enormous shudder in space-time, a collision of different vacua, each with its own energy density and perhaps slightly different physical parameters. Where the bubbles meet, energy could be dumped into radiation and particles. The geometry inside each bubble might be distorted, leaving a lasting imprint on the skies of any observers who arise there later. You tilt your head mentally toward our own sky. If our bubble universe had once collided with another, what would you see? Theorists have played with this question. Some models suggest a bubble collision might leave a circular feature in the cosmic microwave background, a slightly warmer or cooler disk, or a region where the statistical properties of the temperature fluctuations are subtly different. You imagine the CMB not as static fuzz, but as a faint, mottled fresco on the inside of a cosmic dome, with a pale circular bruise where another universe once brushed against ours. So far, careful searches through the microwave sky haven't found a smoking gun. There are hints and anomalies, small patterns that spark debate, but nothing widely accepted as evidence of a bubble collision. The CMB, as best we can tell, is remarkably consistent with a simple inflationary origin, where our region has evolved largely in isolation. If bubble universes do collide, those collisions may be rare, far away, or simply arranged so that their scars are too subtle for our instruments to pick out from cosmic noise. You let that uncertainty settle. Even in a multiverse, direct touching in a dramatic, cinematic way is not guaranteed. Two bubbles might form so far apart in the inflating background that their walls never meet. Others might collide violently and destroy the delicate conditions needed for life before anyone ever looks up at a sky. Then you turn your attention back down to the quantum scale, where many worlds lives. If every quantum event branches reality into different outcomes, you might wonder, could these branches ever interfere again in some noticeable way? Could you get a message from another you? In principle, quantum mechanics allows interference between branches that have not decohered. You picture an ultra-isolated laboratory, colder than deep space, shielded from every stray photon, every molecule of air. Inside, a carefully prepared quantum system evolves, splits into different components corresponding to different outcomes, and then crucially is recombined in just the right way to produce interference fringes. This already happens in real experiments with atoms, photons, even large molecules. Wave functions split and then rejoin, creating patterns that depend on both paths. In the many worlds language, you might say that different branches briefly talk to each other before decoherence separates them. The interference fringes you observe are the visible shadows of that conversation, but notice how fragile this is. The moment the environment records which path a particle took, the moment a dust grain, air molecule, or detector pixel becomes entangled with it, the coherent superposition spreads out into the wider world. Decoherence slams the door on interference between those macroscopic branches. To reverse it, you would need godlike control over every interacting degree of freedom, every photon, every atom, every neuron that got entangled with the outcome. One misplaced air molecule, one rogue thermal photon, and the information you'd need is lost in a fog of correlations. So yes, branches can interfere when they're tiny, protected, and freshly formed. That's what quantum experiments rely on. But once they've grown to include whole measuring devices and conscious observers, their ability to meet again is effectively gone. Many worlds gives you parallel histories, but not parallel timelines you can cross between. No messages, no portals, no quick trips to check on the version of you who made a different choice. You can feel a quiet lesson in that. The universe, as described by our best-tested theories, seems very strict about what kinds of touching are allowed. Fields interact locally. Signals travel at or below the speed of light. Decoherence locks in macroscopic outcomes and hides the deeper quantum branching. Even gravity, which curves space-time itself, doesn't casually tear open tunnels to other universes. Still, scientists keep asking where the limits really are. Could subtle signatures of bubble collisions lurk in future, higher-resolution sky maps? Could exotic gravitational effects hint at higher dimensions or hidden sectors that brush against our own? Could microscopic black holes or other phenomena at particle colliders betray the presence of extra universes nearby in some higher dimensional bulk? If those hints exist, they're buried deep, beneath background noise and experimental uncertainty. That's part of what makes this field so delicate. A multiverse is, by definition, mostly out of reach. If other universes are causally disconnected from ours, then their effect on our measurements will be, at best, indirect statistical, anthropic, or encoded in the logic of the theories themselves. Maybe the universe just loves to keep some doors painted on, never meant to open, only to remind you that the room you're in is part of something bigger. You live in one branch, one bubble, one brain, one possible cosmic story. The rest, if it exists, is like a quiet neighborhood you'll never visit, but whose presence shapes the city in ways you may only infer. And yet, that doesn't leave you with nothing. It leaves you with a strange, beautiful boundary, a horizon not only in space and time, but in knowability. Physics can tell you what would happen if universes collide, or if branches re-interfered, or if brains brushed against one another. It can tell you how such events might leave faint fingerprints in the data we collect. But it also tells you that some kinds of contact, the kind where you step through a glowing doorway into another timeline, or wave at another version of yourself across a shimmering veil, are exquisitely unlikely. Tonight, as your breathing slows and your muscles loosen, you can think of your universe as a self-contained song. It may be one track in a larger album, one melody among many, but the notes you hear are the only ones you get to dance to directly. Other tracks might exist, written into the deep mathematics of reality, but they don't bleed into this one in any obvious way. You can let that be comforting. Your choices, your sky, your relationships are not constantly being overwritten by collisions with unseen worlds or by interference from other branches. The universe you experience is remarkably stable. The stars will rise and set according to the same laws tomorrow as they did yesterday. If there are other universes brushing against the edges of possibility, they do so with a delicacy that leaves your pillow, your heartbeat, and your dreams undisturbed. You're back under a dark, high dome now, not the sky this time, but an observatory roof. In your mind you hear the soft mechanical whir as the slit opens, revealing a slice of night. A telescope turns with slow, heavy grace, and somewhere in the building below, racks of servers hum, turning streams of photons into numbers, into maps, into clues. Tonight's quiet question: how do you ever test an idea about universes you can't see? You let the word test rest on your tongue for a moment. In everyday life, testing is simple. You try a key in a lock. If it turns, the key works. You heat water. If it boils, you confirm something about temperature and pressure. But when the hypothesis is there exist other universes, beyond what you can ever observe, the usual kind of direct check seems impossible. There is no telescope, no rocket, no probe you can send beyond the edge of your cosmic horizon. So physics has to work differently here. Instead of asking, can I go there? It asks, does the theory that predicts a multiverse also make precise, testable predictions about the universe I can see? The multiverse becomes part of a larger package deal. You don't test it in isolation. You test the whole framework that leads to it. You think back to inflation. The same equations that, when extended, suggest eternal inflation and bubble universes also make more modest predictions about our own sky. They predict that space on large scales should be very nearly flat. They predict that the tiny temperature fluctuations in the cosmic microwave background, that faint, mottled glow from the early universe, should have a particular statistical pattern, almost scale invariant, with specific correlations between hot and cold spots. You imagine the CMB map as a soft, speckled sphere around you, colours showing minute differences in temperature, only tens of millionths of a degree. To the eye, it looks like random noise. To a patient computer, it is a rich tapestry of information. Satellite experiments like COBE, WMAP, and Planck have measured that pattern with exquisite precision. The result? The data line up remarkably well with simple inflationary models. Space is very close to flat. The fluctuations look almost exactly like what you'd expect from quantum jitters stretched to cosmic size by a brief burst of ultra-fast expansion. So inflation, the part that talks about our bubble's early history, passes some very hard tests. Once you accept that, you're faced with a choice. You can trim the theory, keeping only the parts that describe our observable patch, and discarding the extensions that lead to other bubbles. Or you can take the theory seriously, wherever its math naturally leads, even if that includes regions you'll never see. The first path feels cautious, the second feels bold. Science, in practice, contains people walking both paths at once. You can see a similar pattern with black holes. For decades, they were purely theoretical solutions of Einstein's equations, living on chalkboards. No one could fly into one to check. Yet the theory that predicted them also made countless other predictions about gravity, light bending, time dilation, and orbital motion, and those passed test after test. With time, indirect evidence piled up. Stars orbiting invisible masses, X-rays from matter heating as it spirals inward, gravitational waves from colliding black holes, even the shadowy silhouette imaged by the Event Horizon Telescope. At some point, most physicists decided, okay, black holes are real, even though the interior remains hidden. Parallel universes, if they are ever accepted in that way, will probably follow a similar route, as indirect implications of theories whose other predictions we can scrutinize closely. You never catch a multiverse in a jar, but you might judge it by the company it keeps. There's another kind of test too, statistical and anthropic. You remember those finely tuned dials, the cosmological constant, the strengths of forces, the masses of particles. In a multiverse where those values vary from region to region, you'd expect most universes to be sterile and lifeless. Observers like you would naturally find themselves in rare habitable patches, where the constants fall in the narrow range that permits galaxies, stars, and chemistry. In the late 1980s, Steven Weinberg and others pointed out something striking. If you assume the cosmological constant takes many values across a multiverse, but life only arises where its value isn't too large, then you can use that requirement to estimate what a typical observer should measure. The answer turns out to be of the same order of magnitude as what we actually see, a tiny positive cosmological constant that lets structure form, but eventually drives accelerated expansion. It's not a sharp prediction, but it's suggestive. The multiverse, plus an anthropic selection effect, explains why this dial is small but not zero, where simpler theories struggled. You picture a universe ensemble as a broad, hazy bell curve of possible cosmological constants. Almost all the weight lies in regions where no complex structures ever arise. A sliver corresponds to universes with galaxies and life. You're in that sliver. The anthropic argument doesn't let you calculate the exact numbers from first principles the way you might with a simpler law, but it does turn a seemingly bizarre value into something less surprising, given the broader context. Some physicists are comfortable with that kind of reasoning. Others are wary. They worry that anthropic explanations might become a habit, a way to stop looking for deeper, dynamical reasons. They ask, when does we observe this because otherwise we wouldn't be here, illuminate? And when does it simply restate the obvious? The conversation flows back and forth in papers, conferences, and late-night discussions in quiet offices lit by fluorescent hum. You realize that testing the multiverse is also about testing the boundaries of what counts as science. We already accept some unobservable entities, quarks, distant galaxies beyond any hope of direct visit, the far side of a black hole, because the theories that invoke them are tightly constrained, make precise predictions, and have survived attempts to prove them wrong. The multiverse stretches that pattern to its limit. Are we willing to grant reality to universes forever beyond our light cone, if the theory that implies them is our best, most coherent description of the part we can see? Maybe the universe just loves to push you up against the edge of your epistemic comfort zone, to the place where experiment, inference, and philosophy meet. You take a slow breath and feel the science become personal again. In a way, you test multiverse ideas simply by doing ordinary cosmology better. By mapping the cosmic microwave background more precisely, by measuring the distribution of galaxies on large scales, by refining our understanding of dark energy, by exploring high-energy physics at colliders and in cosmic rays. Each new measurement tightens the net around the theories that survive. Some multiverse models will be ruled out because they predict too much curvature, or the wrong pattern of fluctuations, or the wrong distribution of constants. Others will remain viable, maybe even favored, not because we've seen another universe, but because we've seen our own with unforgiving clarity. Lying there, you can picture a supercomputer room somewhere, dim, cool, with cables like roots and blinking lights like fireflies. Inside those machines, simulations of universes run, not simulated in the philosophical sense, but numerical models of cosmic structure, of inflation, of dark energy. Researchers tweak parameters, compare virtual skies to the real one, and slowly, painfully, narrow down the possibilities. From your vantage point, in one small room, it might seem that the multiverse is forever beyond you, and in a direct, travel there sense, it probably is. But your curiosity participates in the same long project, trying to understand which stories about reality earn their place not just in our imagination, but in our best-tested theories. As your eyelids grow heavier, the observatory dome above you closes. The telescope parks. The servers keep humming quietly, crunching data through the night. Somewhere, equations that imply other universes sit half-scribbled on chalkboards, awaiting their next test. You don't have to solve them. You only have to appreciate that even questions about unseen worlds are, at their best, anchored to the one world you know, this one, with its CMB glow, its accelerating galaxies, its mysterious constants, and the simple fact that you are here to wonder at all. You're standing now in a different kind of observatory, not a dome on a mountaintop, but a quiet hallway in a physics department at night. The fluorescents hum softly. Posters of galaxies, particle tracks, and equations fade in muted colors along the walls. Somewhere down the corridor, a whiteboard glows under a single desk lamp, covered in symbols and arrows and question marks. This is the place where science and speculation meet. You walk toward the whiteboard. Someone has drawn a rough sketch of a potential energy curve, a scribbled Calabi-Yau manifold, a cartoon of bubble universes budding off from an inflating background. Beside it, in smaller handwriting, are words like testable and anthropic and falsifiable. The chalk dust smells faintly dry and metallic in the cool air. Your question tonight is a gentle but sharp one. At what point does a beautiful idea about reality stop being science and become something else? Philosophy, metaphysics, or just an elaborate bedtime story? You start with a simple picture of science you may have heard before, associated with philosopher Karl Popper. In this view, a scientific theory is one that can, in principle, be proven wrong. It must make falsifiable predictions, clear statements about what you shouldn't observe if the theory is true. When such predictions fail, the theory is in trouble. When they survive repeated tests, the theory earns your trust, though never absolute certainty. You imagine a row of glass beakers on a lab bench, each filled with a different clear liquid. You have hypotheses about what each one is. You design experiments to distinguish them, heat them, cool them, mix them with reagents, shine light through them. The ones that behave as predicted keep their labels a little longer. The ones that don't get relabeled or discarded. The process is tangible, almost tactile. But the universe at its deepest levels doesn't sit in a beaker. With cosmology and fundamental physics, your experiments are often indirect and your theories broad. They're not just about one liquid, they're about the entire set of possible liquids the universe could contain. They reach far beyond the data you can collect in a lifetime, or even in the life of your species, so you add nuance. Another philosopher, Imre Lakatos, described science not as isolated, falsifiable statements, but as research programs, clusters of core ideas surrounded by auxiliary assumptions. When an experiment contradicts a prediction, scientists don't always throw away the whole core. They may adjust the auxiliaries. We misestimated the dust. We didn't account for this systematic error. We need an extra particle in the model. A program is progressive if those adjustments lead to new, successful predictions. It becomes degenerative if they turn into ad hoc patches that only rescue the theory from failure without new explanatory power. You picture a ship at sea. The hull is the hard core of the theory. The planks and ropes are auxiliary hypotheses. When a plank rots, you can replace it without sinking the ship. But if you're constantly patching leaks and never making progress, at some point you have to ask whether this is still a seaworthy vessel. Now you turn back to the multiverse. Eternal inflation, string landscapes, many worlds, baby universes, simulations, all these ideas live out near the edges of what we can observe. They differ in detail, but they share a worry. If their extra universes are forever beyond your horizon, are they really part of science? Or are they decorations on the edge of the map? You feel the tension in your chest like a quiet knot. On one side, you have theorists who say, if a well-tested theory naturally implies a multiverse, we should take that implication seriously, even if we can't directly see those other realms. We already do this with black holes and quantum fields and curved space-time. We believe in them because the broader frameworks that contain them have passed severe tests. The multiverse, in this view, is just another consequence of equations that are already doing hard work elsewhere. On the other side, you have critics who worry that multiverse talk can become unmoored. If you can always say somewhere in the multiverse this happens, you risk draining predictive power from your theories. Instead of explaining why the constants have certain values, you might say because we're in one of the rare universes where those values occur, and stop looking for deeper mechanisms. They fear a slide from physics into something closer to storytelling, where almost anything can be accommodated. You sit with both voices. In your mind's eye, they're two colleagues in that dim hallway, leaning against opposite walls with coffee mugs in hand, talking past midnight. One is drawing curves and landscapes, excited by the mathematical coherence of the framework. The other is tapping a pencil on the counter, asking, "Okay, but what would convince you this picture is wrong? What observation would make you abandon it?" That question, what would change your mind, is a good compass. When an idea is scientific, you can usually at least imagine some pattern of evidence that would favor alternatives. If a future satellite measured the cosmic microwave background and found wild deviations from inflation's predictions, simple inflationary models would be in real trouble, along with many of their associated multiverse pictures. If attempts to embed the standard model of particle physics into string theory never produced consistent solutions, stringy landscapes would look less attractive. Sometimes the test is more subtle. A speculative idea may be judged by whether it gives you new questions to ask, new experiments to design, new ways to tie together previously separate pieces of data. Dark matter is an example. At first, it was a speculative fix for galaxy rotation curves and cluster dynamics. Over time, as it helped explain more and more phenomena, the cosmic microwave background, structure formation, gravitational lensing, the dark matter hypothesis became part of a progressive research program. It moved from patch toward pillar, even though we still haven't caught dark matter particles in the lab. You can ask, will multiverse ideas follow a similar path? Will they generate new, specific observables to look for subtle imprints in the sky, correlations among constants, distinctive patterns in high-energy physics that let us prefer one multiverse model over another, or over no multiverse at all? Or will they remain mostly interpretive layers on top of already tested theories, influencing how we talk about reality more than what we can measure? Your senses pull you back to the present. The faint sound of your own breathing, the weight of your body, the gentle temperature of the room. The boundaries between science, philosophy, and fiction are not written in the stars. They're drawn by humans, in chalk and in journals and in conversations like this. They can shift as new tools and ideas arrive. Maybe the universe just loves keeping you slightly off balance, offering you questions that sit on the threshold between what can be measured and what can only be imagined. So where does that leave you, lying here with parallel universes on your mind? You don't need to judge every idea tonight. Instead, you can learn to hold a spectrum. On one end are hard, quantitative, repeatedly tested frameworks. General relativity, describing GPS satellites and black hole mergers. Quantum electrodynamics, predicting the magnetic moment of the electron to many decimal places. On the other end are free-floating stories with no commitments to data at all. In between, live multiverse models, simulation hypotheses, and other boundary-defining ideas anchored in some equations, reaching beyond available evidence, still negotiating their place in the scientific landscape. The important thing is not to erase that spectrum, but to be honest about where along it an idea sits at any given moment. It's okay for science to have a frontier where speculation is bolder, as long as there's an ongoing effort to connect back to observation, to refine or abandon ideas in light of new information. It's okay, too, for philosophy to walk alongside science there, asking what it would mean if these possibilities were real or forever beyond testing. As your thoughts slow, the hallway darkens. The whiteboard fades to grey. Somewhere, actual physicists are working late, balancing creativity and discipline, imagination and skepticism. They're trying to keep their theories close enough to the world to be tested and wild enough to reveal something new. You don't have to solve the demarcation problem between science and non-science. You only have to carry a gentle awareness that not all claims are equal, that some are more tightly linked to evidence than others, and that it's okay for some ideas like parallel universes to live for a while in that liminal space, inspiring wonder while awaiting their final status. You can let that awareness cradle you as you drift, the sense that humans are still learning how to ask good questions about a universe that might be more layered than your current tools can penetrate. The boundary between science and speculation isn't a wall. It's a shoreline, with waves of curiosity washing back and forth. Tonight, you stand barefoot at that edge, feeling the cool water curl around your toes, before you turn back toward the solid sand of sleep. You're still in that dim university hallway in your mind when you notice another kind of poster on the wall. Not data plots or equations this time, but movie posters. A man in a red and blue suit, swinging between skyscrapers. A woman with a third eye opening in her forehead. A team of superheroes assembling in front of a cracking, glowing sky. You step closer. The multiverse has slipped out of chalkboards and into stories. You've probably met parallel universes first this way. In films, comics, anime, games. You remember flashes of scenes, a character stepping through a portal into a world where their life turned out differently, or tumbling between realities like pages riffled in a book. In Spider-Man, Into the Spider-Verse, many versions of the same hero meet. Different costumes, different personalities, same underlying identity. In Everything Everywhere All at Once, jumps between universes are triggered by absurd little actions, like switching shoes or saying the wrong thing on purpose, each choice snapping you onto a new track. In the Marvel stories, timelines branch, collide, get pruned, and stitched together again. These stories are loud, bright, kinetic. You can almost hear the crackle of energy when a portal opens, see the confetti of broken glass and shimmering light as realities collide. They're fun because they take your everyday what-ifs. What if it'd chosen differently? What if it'd stayed? What if it'd left? And turn them into literal travels. The alternate you is not just a thought experiment. She's standing right there, arguing with you, hugging you, sometimes trying to punch you. Myths did something similar long before physics or CGI. You can drift back, in imagination, to ancient storytellers sitting by firelight. In Hindu cosmology, there are many lokas, realms of existence stacked and interwoven, gods and humans, and other beings living in different layers of reality. In some Buddhist traditions, beings move through multiple worlds and planes according to karma, like travelers on a vast spiritual map. Norse myths speak of 9 worlds connected by Yggdrasil, the world tree, realms of gods, giants, humans, and the dead. These are not multiverses in the modern scientific sense, but they rhyme with the idea. They say, what you see is not all there is. Beyond your village, your planet, your sky, more realms exist, with different rules, different inhabitants, and paths sometimes difficult, sometimes dangerous between them. You stand in front of all these stories and feel a familiar human hunger. We seem to love the thought that our world is one layer in a stack, one room in a mansion, one branch on a tree. Maybe it's because life itself feels like that, past, present, and future selves, that you can never all occupy at once. Choices you made and didn't make. Paths your life did and didn't follow. The multiverse becomes a mirror for regret, hope, and curiosity. Then you quietly ask, how do these fictional and mythic multiverses compare to the ones suggested by physics? You notice the first big difference: access. In almost every story, characters can cross between universes. They build machines, cast spells, fall through wormholes, or perform strange rituals. Worlds are connected by doors, portals, or at least some navigable path. Drama depends on that. Without crossovers, you can't have a team-up of alternate heroes or a confrontation between different versions of yourself. In most scientific multiverse ideas, by contrast, access is precisely what you don't have. Bubbles formed in eternal inflation are separated by inflating space that pushes them apart faster than light, cutting off communication. Many worlds' branches decohere into non-interfering histories. After that, there's no known physical mechanism for hopping between them. Brain worlds in higher dimensions might be separated by warped geometry or extra-dimensional distance with no known bridge. Parallel universes in cosmology are parallel in the sense of being causally disconnected, not side-by-side rooms with doors. You can think of it like this. Fiction's multiverse is a network of subway lines with adventurous transfers. Physics, multiverse, if it exists, is more like a collection of sealed train cars that never share doors, only a manufacturer. The second difference is rules. In many stories, hopping universes can ignore or bend conservation laws to serve the plot. People and objects appear and vanish between worlds without worrying about where the extra energy came from or how causality is preserved. Time travel, alternate histories, and multiverse crossings mix freely. Real physics is stricter. Energy, momentum, charge, and other conserved quantities can't simply pop into existence in one universe because they disappeared in another, not without a very specific, well-defined mechanism that respects the underlying laws. Even exotic ideas like wormholes, if they exist, are constrained by general relativity and quantum field theory. They must obey equations, not just narrative convenience. You remember the quiet, careful work of decoherence in earlier sections, how quantum branches peel away from each other because information about outcomes gets irreversibly spread into the environment. That process gives you many worlds in principle, but it does so in a way that's continuous, lawful, and, for all practical purposes, irreversible. It doesn't create magic doors. It creates consistent, non-communicating histories. And yet, there are deep similarities too. When a film shows a branching timeline where every choice creates a new world, it is echoing the logic of many worlds, even if the details are off. When a story plays with different versions of a character, one who was brave, one who was afraid, one who stayed, one who left it, is dramatizing something that the mathematics of quantum mechanics also suggests, that possibilities can all be realized somewhere in a larger structure. You can let the two layers sit together without forcing them to match perfectly. The scientific multiverse, if real, behaves according to equations. The fictional multiverse behaves according to narrative needs. One is constrained by experiments, the other by emotions. Maybe the universe just loves being retold. Myths, religions, fictions, and physics are all, in their own ways, attempts to weave a coherent story around the raw, unsettling fact of existence. You also notice how stories influence your intuitions about science. When you first hear someone mention parallel universes, your mind might jump to your favorite multiverse movie with its portals and variants and spectacular crossovers. That's understandable. But it can also make real physics feel disappointing. What do you mean, no hopping between timelines? Or it can make fragile, speculative ideas feel more solid than they are, because your emotional memory of the story is strong. So part of the gentle work, as you lie here listening, is untangling those threads, letting yourself enjoy the stories, while also recognizing that they aren't evidence. Fiction can inspire hypotheses, but experiments and observations still have the final say in science. At the same time, you don't need to sneer at the myths and movies. They serve a different purpose. They let you inhabit the multiverse emotionally. A scene where two versions of a character share a quiet moment, perhaps one successful, one struggling, says something about regret, resilience, and identity that equations alone cannot. You might never be able to step into a universe where you made another choice, but you can, in imagination, visit those branches of your own life, feel what they would have been like, and return with more compassion for the version of yourself who ended up here. Multiverse stories give that inner process of visual language. As your eyes grow heavier, you can picture yourself sitting in a dark cinema, the only sound a soft rustle of popcorn, the screen painting worlds on your retinas. On that screen, universes collide, branches reunite, gods travel between realms on rainbow bridges. In your lap, your hands rest warm and still, attached to a body that obeys quieter, stricter laws. You don't have to decide which picture is better. You can let them coexist. Physics to tell you what the universe probably does. Stories to help you feel what that means. When you step out of the theatre, or close the streaming app, or put down the comic, you return to one world. This one, with its specific sky, its particular people, its unrepeatable days. Whether or not parallel universes exist out there, you live in precisely this branch. Fictional multiverses remind you that things could have been different. Physics reminds you how delicately structured they already are. Between them, maybe you find a gentle middle place, gratitude for this single, bounded life, and curiosity about the many ways reality can be imagined, even if only a subset can ever be measured. You're still sitting in that dark cinema of the mind, the credits of countless multiverse stories drifting upward, different versions of heroes, different choices, different outcomes, all glowing briefly on the screen, then fading to black. When the light comes up, though, it's just you and your one life again. A quiet question waits there, like a coat on the back of your chair. If there are parallel universes, if other branches exist where you made different choices, what does that mean for this you, right here? You let the question settle. You picture yourself as a small figure on a high balcony, looking down at a branching river. Each fork is a decision, to say yes or no, to stay or go, to speak or stay silent. In some multiverse stories, every fork is taken somewhere. In many worlds, quantum mechanics, every outcome allowed by the wave function is realized in some branch. If that's true, you might wonder, does anything you choose really matter? Is there always another version of you who did the opposite, no matter what you decide? You feel a flicker of unease in your chest, then you breathe around it. Start with something simple. Even if there are other branches, you only ever experience one. The you listening to this right now has a particular history, specific conversations, specific mistakes, specific small kindnesses. The fact that some other branch might contain a different sequence doesn't erase this one. Just as the existence of other people doesn't make you less real, the existence of other versions of you, if they exist, doesn't make this version less real either. Think of a library. Each book on the shelf is its own story. Knowing there are other books doesn't drain meaning from the one you're actually reading. Within that book, the characters still face stakes, make choices, live with consequences. Many worlds, if you take it literally, says reality might be a cosmic library of histories, but you are still reading one particular book from the inside. There's a factual point here, grounded in both physics and philosophy of mind. Your sense of self is tied to a specific, continuous chain of brain states, neural patterns connected by memory, perception, and bodily continuity. Those patterns live in one branch at a time. You can't feel the alternatives. You can't wake up tomorrow with memories from a neighboring branch where you made a different choice. Your psychological identity, the I that worries and hopes and plans, rides one stream. Now you imagine an everyday decision. It doesn't have to be life-changing. Maybe it's whether to send a kind message to someone who's been on your mind, or whether to take a small risk on a project you care about, or simply whether to put your phone down and rest. You hover in the moment before choosing, feeling the familiar tension, part of you leaning one way, part the other. In a simple, single universe picture, you might say, only one of these possibilities will become real. In a strict, many worlds picture, you might say, branches will exist where you do each thing. But notice what doesn't change either way. In this branch, your future still depends on what you do. If you choose kindness here, this version of the relationship changes. If you choose fear here, this version of the story goes another way. Whatever happens in other branches, the people around you in this one will feel the warmth or the absence of what you decided. So when philosophers talk about responsibility in a branching universe, many of them keep it local. They say, you are responsible for what this copy of you does in this history, because those actions causally shape the world you actually inhabit. The fact that other copies act differently elsewhere doesn't cancel that. It's a little like having identical twins. One twin's missteps don't absolve the other from their own choices. You can feel this in your body if you pay attention. Think about a time you apologized, or helped someone, or did something you're quietly proud of. The warmth or relief you felt afterward lives in your nervous system. Relaxed shoulders, easier breath, a softer jaw. That's not an abstract, multiverse-spanning property. It's concrete, measurable physiology in this one organism, in this one branch. At the same time, the multiverse idea can soften a particular kind of self-torment. When you look back and think, if only I'd done X instead of Y, everything would be different. You're running a personal alternate universe simulation in your head. In many worlds, language, that alternate outcome, is realized somewhere in the wave function. But you're not there. You're here, with this history. Maybe that realization can be oddly compassionate. Instead of obsessing over the roads not taken, you can imagine that somewhere in the mathematical structure of reality, versions of you did explore them. This doesn't fix your mistakes, and it doesn't excuse harm, but it can nudge you away from endless what-if loops. In this branch, the only direction you can actually move is forward, from this moment. There's another factual thread to weave in. Psychological research on the sense of agency suggests that what matters for your experience of meaning is not whether your choices are metaphysically unique across all reality, but whether you perceive yourself as able to influence outcomes in your environment. When people feel their actions have no effect, whether because of external constraints or inner beliefs, they tend to become passive, anxious, or depressed. When they regain a sense of agency, even in small ways, well-being tends to improve. In other words, your brain's health and your life's texture depend more on how you relate to your choices than on what deep metaphysical model of the universe you endorse. A branching multiverse can be framed in a way that preserves agency. I still shape this branch. Or in a way that erodes it. Nothing matters because somewhere I do everything. The physics doesn't force the second framing. That's an interpretive layer you can choose to adopt or gently set down. Maybe the universe just loves offering you perspectives that can heal or harm, depending on how you hold them. You can also turn the question around. If the multiverse exists, then every ordinary act of care happens not once but countless times across branches. Helping a stranger, listening to a friend, tending a garden, caring for someone who is ill. In some interpretations, that means the cosmos is thick with these acts. Your small kindness tonight is one bright pixel in a vast, repeating pattern of kindness. That doesn't make it redundant. It makes it part of a larger chorus. From the inside, though, it's still just you, deciding whether to send that message, to forgive, to rest, to show up. No one else, in this universe, can substitute for that. As your eyelids grow heavier, you can picture your life not as a fragile, isolated thread, but as one visible strand in a great woven fabric of possibilities. Parallel universes, if they exist, don't erase your responsibility. They just say that the fabric is larger than you thought. Your task doesn't change. To make this strand as honest, kind, and awake as you can, given your limits and your circumstances. There will always be questions you can't answer about free will, determinism, branching, fate. You don't have to solve them before you sleep. You can let them sit like distant constellations, beautiful to look at, too far away to touch tonight. Closer in, near the horizon of your day, are simpler stars. The people you care about, the things you value, the next small choice in front of you. You can choose, gently, to honor those. Here, in this one universe, you actually feel under your fingertips. By now, you've traveled a long way without moving at all. You've drifted from the edge of the observable universe back to the first fractions of a second after the Big Bang. You've shrunk down into quantum fog and hovered near the event horizons of black holes. You've walked winding paths through string landscapes, stepped cautiously past racks of hypothetical cosmic servers, and sat quietly with philosophers in fluorescent halls. And then, each time, you've returned to the same place. Here, one body, one room, one universe you can actually touch. You notice that. The bedsheet under your fingers, the gentle pressure where your body meets mattress or chair, the temperature of the air on your face. Parallel universes, if they exist, are somewhere out on the far edges of theory and possibility. This fabric under your hand is not. It's immediate, specific, undeniable. You breathe in, slowly. The air carries molecules exhaled by trees, by oceans, by people who lived before you were born. Photons that left the sun 8 minutes ago warm the side of the planet you're on, drive the weather that rattled your windows today, whisper into the climate your descendants will inherit. Gravity, the same force that curves space-time around black holes, curves space-time gently around your body too, holding you to the earth with just enough strength to feel secure but not crushed. That's one quiet fact to carry. The laws that might generate multiverses are the same laws that keep your everyday world running, moment by moment. Quantum fields vibrate in your neurons. General relativity guides the satellite that helped your phone find the time. Nuclear physics burns in the heart of the star that set the rhythm of your day. If some version of a multiverse is real, bubble universes from inflation, branches from quantum measurements, valleys in a string landscape, then you live inside one particular realization of those laws. This universe is not a rough draft. It's a finished, ongoing chapter. It has a specific history, 13.8 billion years of expansion, of stars lighting and dying, of heavy elements seeding space, of planets forming, of chemistry growing more intricate, until it could support cells, nervous systems, minds, and finally all the stories you tell about what it means to exist. You may never know, in any decisive way, whether other universes share those laws, or twist them, or rewrite them entirely. The evidence might always be indirect, filtered through statistical arguments and theoretical consistency. Science is honest about that. It can show you where its grip is firm and where it starts to loosen, shading into educated guesswork and metaphor. But that doesn't make the journey meaningless. In fact, it's part of what makes it beautiful. Science is not a catalogue of final answers. It's a way of staying in conversation with the universe. Observations, theories, simulations, failures, corrections, all of them are like sentences in a long letter exchanged between mind and reality. Sometimes the reply comes as a crisp number from an experiment. Sometimes it comes as a silence that says, "Not yet." Maybe the universe just loves that kind of dialogue. You ask, it answers a little. You refine the question, it answers a little more. And somewhere in that back and forth, your sense of wonder keeps deepening. You can feel that wonder physically. Psychologists who study awe find that when people contemplate vast things, starry skies, deep time, towering mountains, even complex ideas, their usual sense of self can soften. Heart rate adjusts, breathing slows, attention widens. Problems that felt huge shrink a little in the face of larger scales. The feeling doesn't solve everything, but it can rest you, reset you, like a long exhale after holding your breath too long. Right now, the vast thing you're contemplating is possibility itself. Universes beyond your horizon, branches beyond your experience, levels of structure beyond your instruments. You don't need to hold all the details in your head. You can simply let the idea of more than this sit at the edge of your awareness like a dark, calm sea. And here is where the wind down begins. Imagine the camera of your attention slowly pulling back. First, you see yourself from just above, your face relaxed, eyes half-lidded or closed, shoulders softening. Your device glows faintly, then dims as you set it aside or let it fall still in your hand. The noises around you blend into a gentle background, a fan, a distant car, night insects, the low murmur of pipes or wind. The view pulls back further. Your building shrinks to a small rectangle of shadow in a larger neighborhood. Other windows harbor other lives. Someone reading, someone arguing, someone laughing, someone already asleep. Clouds drift overhead, glowing faintly with city light or pale under the moon. Above them, aircraft trace thin, temporary lines across the sky. Above those, satellites skim silently, their orbits precise, locked in by the same gravity that holds you where you are. Higher still, your country becomes a pattern of coastlines and rivers and mountain ranges, then a swirl of weather, then a soft, lit marble turning against black. Night and day divide the globe in a moving line. Thunderstorms flicker like distant neurons firing. On the sunlit side, oceans breathe vapor. On the dark side, cities sparkle like constellations fallen onto the ground. Keep going. The Earth becomes a point, orbiting a medium-sized star in a spiral arm of the Milky Way. Our galaxy becomes one among billions in a cluster, then in a filament of the cosmic web. At each scale, structures that once seemed enormous become part of something larger and more delicate. Somewhere in that web is the little branch where you are, tonight, thinking about all this. And then, imagine the view stopping not because there's nothing beyond, but because you've zoomed out enough for now. The universe is still here, quietly working while you sleep. Stars are fusing hydrogen into helium in their cores. Supernova shockwaves are sculpting nebulae. Black holes are slowly feeding or quietly evaporating. Quantum fields are humming at every point in space. Plate tectonics is nudging continents, centimeter by centimeter. Life is budding, growing, resting, ending, beginning again in places you will never see. None of this depends on you being awake to supervise it. That can be strangely comforting. While you sleep, gravity will still curve space-time. The constants will keep their values. The cosmic microwave background will continue its long, slow cooling. If there are parallel universes, they will continue whatever histories they're following, far beyond the reach of your dreams. Your job, tonight, is much simpler. It's to let go of the need to solve any of this before morning. You can set down the questions about whether other universes exist, about whether your choices ripple across branches, about where science ends and story begins. You've honored those questions. just by holding them gently in your mind for a while. Now you can trade big thoughts for small sensations. The weight of your limbs, the feel of fabric, the rhythm of your breathing, the way your eyelids grow heavier with each exhale. If stray ideas surface about the day behind you or the days ahead, you can imagine them as tiny bubble universes of their own, drifting through your mind's sky. You don't have to chase them or pop them. You can watch them appear, glow briefly, and then fade into the background. Somewhere, scientists will keep working through the night. Telescopes will keep tracking the sky. Detectors will keep counting particles, and equations will keep waiting on blackboards. Reality will go on being real, in all its known and unknown layers. You, for now, are allowed to rest. Let your thoughts thin out, like stars disappearing behind a slowly brightening fog. Let your body sink a little deeper into whatever holds it up. There is nothing you need to do, nowhere else you need to be. This one universe is enough for tonight.